a little bit more about rates and, in fact, the collision theory. And we've got a few bullet points here, Miss McLaren. But when you think about a reaction, it can only happen when the reactant particles collide. Now, Miss McLaren, do you know what collide means?
Well, that just means when the particles bump into each other.
Oh, okay, so they're bumping into each other all the time. The reaction is going ahead, the particles are bumping into each other, but not every bump leads to a reaction.
No.
Why might that be?
Well, I actually thought they did, but now that I think about it, is it because when they bump into each other, there's not enough energy for a reaction to occur?
Absolutely right. They all need a certain amount of energy, a minimum amount of energy or more than that, before a successful collision can take place. And that energy's got a special name, Miss McLaren. What would that be?
Here's something I prepared earlier, as per usual. And we have, it's a particular energy called activation energy.
Perfect. So, lots of collisions are going on all the time, but unless the particles have at or above the activation energy, and that's a phrase you need to know, the collision will not be successful. And when you talk about collisions, it has to be a rate. So it's successful collisions per unit time.
Again,
so
another one I prepared.
This per unit time is very important to include in your answers. It's successful collisions per unit time.
Dr. Blunt, is that because we're measuring rate, so we always have to include time?
Absolutely.
Can we also mention frequent successful collisions? Would that mean the same thing?
Yeah, if you use frequency as another time phrase, that would be fine.
Oh, fantastic.
More frequent successful collisions would be absolutely fine.
Or successful collisions per unit time.
Yes,
I think we've got the idea of this one.
Okay, so now we're happy that there are some collisions that are not successful, so no products are produced from that, and there are others that are successful. But there's another twist, as you know from the graphs you saw in the last vlogs, that as the reaction proceeds, it slows down. Can you think why that might be, Mr. Tanner?
Well, if you have the reactant particles and they have enough energy for them to react successfully,
yes,
then that means there's less reactant particles. Is that correct, Dr.
Right, so you're saying as the particles react, they're used up.
They're used
They
up.
become products, so there's less reactant.
So that means there's less collisions
Yes.
of reactant particles, which means there's less successful collisions per unit
time. Absolutely right. So at the very beginning of the reaction, when it's fastest, at the steepest bit of the curve, there are lots and lots of reactant particles all colliding, some of which will be successful. But as those successful collisions occur, it takes reactant particles out of the mixture, and so you're then left with fewer reactant particles to collide. So therefore, the whole reaction process will slow down.
And Dr. Blunt, just a final question, because I think I've got the idea of the collision theory. When does the reaction finish?
Aha. Now, if you imagine all these particles have to find something to collide with. Now, so you have a reaction with two reactants. Once one of those reactants has all been used up, then there's no possibility of any more reaction because nothing for the other reactant particle to bump into.
So that just means one of the reactants may collide with itself. But
no reaction.
There's no reaction.
Yeah.
Well,
Okay.
I think we actually sorted out rates.
I think that's it. That's it. Job done.
Sorted.